Hello, everyone. I'm Fahad, and I will be going through the lecture for subsurface fluid flows, hydrology of geothermal systems. This is chapter 4 from the Geothermal Energy book by William E. Glossley. Geothermal energy, compared to its peers, whether they are renewable energy sources or traditional energy sources, is quite underdeveloped and under-researched. There are many reasons this is true, however, the difficulty in researching modeling geological systems is the main reason. So, it takes a lot of time and money to study a geological formation or even a rock formation and to get the required data to adequately get enough fluid flow from these geological formations. And so that is probably the main reason why it is quite underdeveloped and under researched. And there are a lot of approximations involved in this field in general. Um, and so that's mainly why there's a lot of difficulty in this. The two main factors involved in geothermal energy generation are the temperature and fluid flows. This chapter will be exploring all the details involving the latter. So, this chapter is all about fluid flow in these geological formations. Concepts of permeability, porosity, and everything that surrounds them are the main focus that we will be discussing. The general model for subsurface fluid flow. Advanced understanding of geological formations of drilling sites or points of interest are essential for the complex procedure of extracting heat and generating geothermal energy. 2 points could be relatively close but exhibit extremely different behaviors. So, 2 points can be as close as 100 meters apart, yet exhibit extremely different behaviors. So, a study for a site has to be specific for a certain region, a certain area. And this is, of course, different for different types. Like, some regions exhibit very similar behaviors according to their location, according to their elevation in general, like a flat surface over a very long range would probably exhibit similar behavior, but uh, uh, forests or mountain regions are probably places where geological formations are going to be very different from in for the specific location. One of the main determining factors are the types of rocks that the fluid is moving through. There are three main rocks in general: igneous, sedimentary, and metamorphic. Igneous rocks are essentially melted rock that have been cooled down over long periods of time. So either from volcanoes or due to volcanic eruptions over time. Um, they probably have been exposed to lava and have melted, or due to extreme heat. Sedimentary comes from rocks that have been that experience water deposits. Some people refer to them as water pockets and or erosion that give them that shape. Metamorphic rocks are either of the previous two, so either igneous or sedimentary, and have been exposed to really high pressures or really high temperatures over very long periods of time, which is why they have a branded appearance usually. Like you can see on the picture on the far right, they usually have similar lines that go through in certain areas. Matrix porosity and permeability. These are two really important factors when it comes to fluid flow in general, and specifically for geological fluid flow in geological formations. Now, what is porosity? Porosity is a physical feature that expresses the amount of open spaces within a formation or a rock. Porosity, unlike other measurements like speed or temperature, varies greatly depending on how you look at it. So, Measurements like speed or temperature are sort of, they don't have many ways to look at them. It's sort of a measurement that is independent of how you look at it, whereas porosity can greatly differ depending on how we are taking porosity into account. And this is something that we'll further explore throughout this lecture. Yeah, two different rocks could have the same porous volume, but one would have a much greater flow than the other because of where the pores are placed or how many they are. And another important factor in porosity is interconnected, is how interconnected the core spaces are. And the reason it's called matrix porosity is because there is more than one layer involved in the concept of porosity. This picture on the left is a description. It clearly shows what the definition of porosity is. In the far left, there are no pore spaces whatsoever. It's completely solid. Nothing can flow through. While in the middle, there's a little more space, and on the far right, it's pretty porous. There's a lot of room for fluids to flow through. Now, the other important concept is permeability. So what is permeability? It is the measurement of fluid movement within a given rock or formation. It is a directionally dependent or anisotropic measurement. Similar to porosity, permeability alone cannot be a sole factor in defining how adequate a rock formation or a geological formation is for extracting geothermal energy. Permeability is dependent on the formations, locations, and sizes of the pores. Furthermore, it also depends on grain sizes, surface tensions of the water, and the absorption and saturation levels of these formations that we'll be looking at and discussing. And this picture on the right here sort of gives a clear depiction of what permeability is as a concept alone. So if you look at the gravel sample on the far left, we're getting the greatest flow out of these three samples, and that's because the grain sizes in the gravel are much bigger, leaving more bigger pores, bigger independent pores. So even though gravel and fine sand can have the same overall porosity, so they may have the same open volume within that specific section of a formation, the amount of fluid that flows through it does not necessarily have to be the same just because the pore volumes are the same. And on the far right, you can see clay or solid rock, which is impermeable or has very, very little permeability. An example of how these two different measurements are intertwined would be how much water seeps into the ground for a receding wave. So the picture on the left, even though quite unclear, you can see it's a beach with coarse grained sands. So the grains here are bigger. When a wave approaches the shore, the water seeps through the sand because there's much more permeability as it goes through. So you can clearly see the water falling through or sort of being swallowed in the shore, depending on how saturated it is, and the foam just staying above shore for a while or deforming. And on the right is a beach shore with completely fine sand. Fine sand for some receding waves, especially if they are moving in faster motions, can seem like it's just flowing through solid ground because it's fine sand and the grain sizes are so small and the openings are so small that it's not permeable at all. So it sort of gives you the illusion that the wave is going through solid ground and coming back. Even though some of the water does flow through the sand, it's not It's a very little amount, and that's what gives the illusion of solid ground. Moving on, mathematical descriptions are not exactly accurate. However, they do give us the best chance we have. As I said before, this is a concept that's really, or this is a field that is quite complex, and so mathematical and physical models always have some kind of inaccuracy, depending on how well studied the geological formation is. The only reason we have geothermal applications is because of these approximations, however, so we still have to depend on them, we still have to use them to the best of our abilities and to the best of whatever research is available to us. Pore space availability is also dependent on water saturation levels. So, for example, in a place where there's a lot of rain and it's very low elevation, fully saturated water conditions can be found much easier and in a much shallower depth. As you can see on the picture on the right, there is what is called a vadose zone. Now, the vadose zone is the zone where the geological formations or rocks are unsaturated. And then the line that separates the vadose zone and the zone of saturation is called the water table. And so below the water table, all of whatever formation that exists there is completely saturated with water, and there's usually going to be water flowing there. The rock's ability to drain or retain water is called the capillary suction potential, and this is dependent on the pore geometry and the surface tension of the water. Even in the vadose zone, rocks are rarely ever completely dry. The rare condition in which formations are completely free of liquid water is when there are unusually elevated temperatures relative to the location. So this is a concept that's kind of, I mean, you can kind of think about it and you'll get it, because since there is a water table below the vadose zone, and since there is a saturation level below that, at least the rainwater will have to go through that vadose zone and go and seep into the water saturation level, if it ever reaches there, honestly, because as we said, depending on the capillary suction potential of the formations that exist in the vadose zone, that depending on the rocks or the material that exist and their capillary suction material, we don't know how dry or unsaturated the vadose zone can be. Fluid movement through geological formations is naturally reliant on many factors, as we have discussed pretty recently and as we will further discuss as we go through this. But the major ones are pore sizes, pore interconnectedness, complexity or tortuosity or pathways, orifice sizes, and the viscosity of the fluid. So there's a lot that goes into this. This picture on the left right here depicts the importance of interconnectedness of water. So even though the two figures A and B, have the same porosity, as in they share the same open volume, which is 40% of the formation, the permeability or the fluid flow that is accessible is completely different between the two. Because the one on the right, because the pores are interconnected, the fluids can flow much faster and much easier. Whereas on the left, even though it does share the same porosity, it's not connected. Or because the pores are not connected, you're not going to receive the same fluid flow. Of course, viscosity of the fluid will change depending on the temperature of the fluid or of the water, and as we were discussing before, how saturation levels in the Vadose zone are variable. They're rarely going to be completely dry unless some natural event occurs where unusually high temperatures are experienced in the Vadose zone. So viscosity of the fluid is also an important factor in determining how fast the water can flow through. Now to start with the equations that are related to this chapter. We're going to start with the fluid flow equation. This equation was formalized by Henry Darcy in the mid-19th century, and it describes the fluid flux through a porous medium. So through whatever geological formation or rock formation. Capital Q represents the volumetric fluid flow, meters cubed per second, and A represents the cross-sectional area, meters squared, that we are specifically interested in. The delta P minus rho GZ term expresses the pressure gradient, including that has to do with specific gravity of water. So it takes into account the specific gravity of water. Other fluid flow equations would take into account just the specific weight of whatever fluid is flowing. As you can see, there are two parts to the equation, so you can either solve it just using the volumetric fluid flow over the cross-sectional area if that information is available to us, or the longer, more extended version includes the permeability, which is K, and the dynamic viscosity, which is mu. So it's negative K over mu times the pressure gradient over L, which is the length of the formation that we're interested in. This equation, however, is only accurate for relatively slow fluid flows, so laminar flows. If we're looking at faster or more complex situations where terminal flows exist, this equation can be used as an approximation, but its accuracy is going to decrease greatly. But for hypotheses and theories, this fluid flow equation can be used even for turbulent flows, but it'll just give you a very broad and general idea, and should not be actually used for industrial applications. Now we're going to look at two equations that express permeability. Kanzi-Kármán equations help approximate permeability values. These two equations take into account everything discussed previously in this presentation to more accurately determine the permeability. The latter, which is the second equation, takes into account tortuosity more specifically. But since tortuosity times the constant characteristics of the system, or C0, is usually 0.2 approximately, in most cases the second equation will be reduced in the form of the first one. So just to take a look at the first one, K equals n cubed over 1 minus n all squared, all over 5 times SA all squared. So here n is the porosity as a fraction, and SA is the specific surface area of the pore spaces per unit volume. So it's kind of straightforward in a way, because it directly involves the surface area with the porosity of a specific formation. Now the second one would give more accurate results, since tortuosity can be very variable depending on what formations we are looking at. The units of permeability can differ depending on applications. The most commonly used is the Darcy, or more specifically, the milli-Darcy. 1 Darcy is defined as the volumetric flow rate of 1 centimeter cubed over 1 second of fluid flow with a viscosity of 1 centipoise through a cross-sectional area of 1 centimeter cubed or squared under a pressure gradient of 1 atmosphere per centimeter. So, as you can see, these units that 1 Darcy is based on are pretty big, especially when taking into account that permeability units a lot of times will be used for sample sizes and testing. So the Miller-Darcy would be a much more efficient unit used in those aspects. Now, another another way to analyze geological formations, or actually another way that geological and rock formations exist, are fracture, porosity, and permeability. Now, before we were looking at systems that were dominated by a matrix porosity, whereas here we're going to start to look at formations that are dominated by fracture porosity. Hydraulic conductivity K is the measure of the ability for rocks to allow fluid to pass. It is equivalent to the proportionality constant in Darcy's law, K, which is permeability over mu, which is dynamic viscosity times the specific weight. And it's expressed in meters over second, so kind of like velocity. Similar to permeability, it is an anisotropic, meaning it is directionally dependent. Now, here it can kind of seem like hydraulic conductivity is very similar to permeability, but it is a little more than that in the fact that it takes into account the fluid itself that is moving rather than just how permeable a layer is. As you can see, it's taking into account the dynamic viscosity of the fluid and the specific weight. It's only natural that hydraulic conductivity would be anisotropic because it's dependent on permeability, which also in nature is anisotropic. A major factor in permeability are the fractures that are present in formations that act as a medium for the fluid flow. These fractures occur for a variety of reasons, and even though some sets have similarities, variable fracture sets are always present. So, like everything we've discussed so far, fractures and the existence of them is something that occurs because of nature and a lot of time, high pressure, high temperature, exposure to many different things. So even though some sets in formation, some sets in formations actually do exist and can have similar attributes, but they're only specific to a rather smaller area rather than looking at one fracture set can be a bad idea sometimes, because you looking at that and extrapolating that and applying it to the rest of the formation can give extremely inaccurate results. The open spaces in fractures are called apertures, and they heavily affect the permeability of certain formations, or actually, and by certain formations I mean formations that are fracture dominated rather than matrix dominated. Some geological systems are dominated by a pore matrix and others by fracture porosity, or by fractures in general. Now, we're going to look at equations that have to do with the fracture hydraulic conductivity K. The first equation on the top left right there, developed by Baer in 1993, is one of the most accurate methods today that can approximate a value for the fracture hydraulic conductivity given the extremely complex nature of this measurement. It relies mainly on both the fracture apertures and spacing. To the extent of our knowledge today, these two factors are the most influential for this measurement. So, the openings of these fractures and how far apart they are or how interconnected they are is the most influential factor in the measurement of fracture hydraulic conductivity. K of Fr, which is just the Fr here is just a symbol for the fracture, equals rho times G over mu times A squared over 12. And A here is the aperture, and just in meters. Behr's equation is comprised of both the equation of hydraulic conductivity and the fracture permeability. So the hydraulic conductivity, with its the hydraulic conductivity alone is going to be the one on the bottom. I apologize for the wrong wording, but yeah, the one on the bottom is just the hydraulic conductivity, not for a fracture specifically, and then the equation in the middle is the permeability of a fracture. So as you can see, it's the same equation, but the only factor that has changed is the fact that we're not using normal permeability, but we are using the permeability for of a fracture specifically. One last big concept in fracture-dominated geological formations or rock formations is transmissivity. Now this is a measurement of how much fluid would be allowed to pass through a certain medium. It is also referred to as the cubic law due to its dependence on the three-dimensional nature of apertures. It looks at the volume as a whole without being able to take into account the interconnectivity, meaning it does not express the actual fluid flow through the formation. So it's another measurement that sort of allows us to determine how likely or how easy it's going to be for the fluid to actually move. And from the concept of fracture transmissivity, we get the concept of effective aperture, which expresses the common and interconnected apertures in which the fluid will flow. However, it cannot be calculated until a value for the fluid flow has been taken into account. So, effective aperture is a really important concept in permeability, but we're only able to get it if we actually have real data and we have all of the other required information. So it's not a value that we can approximate or calculate unless we have everything else. So if we have that value, we can use it for the rest of a formation, assuming that the same material and the formation is exhibiting the same aspects and properties throughout a large area. We can use this effective aperture measurement to more clearly see or more clearly calculate how much fluid flow is going through, because it takes into account interconnectedness. So for example, there could be 5 apertures, each, let's say, 30 centimeters long, but only 2 of them are interconnected. So the effective aperture would only take into account the 2 that are interconnected with the main fluid route that we're trying to pull the water through. Effect of depth on porosity and permeability. In general, porosity decreases as the depth increases, which in turn can decrease permeability as well. The specific measurements rely on the specific locations. So rule of thumb is porosity is going to become less as we go deeper into a formation. Now, even though we have emphasized before how porosity and permeability are not necessarily interconnected, you can have the same porosity for two different formations and two extremely different permeability ranges. However, in whatever formation you look at, if the porosity will decrease, that means that permeability will have to decrease as well, because permeability, as we mentioned, is going to really rely on interconnectedness of pores or of apertures. So, if an aperture is our if these apertures or pores become smaller because the porosity is decreasing, and the permeability will have to decrease as well. The transmissivity equation in the previous slide can be recast as Q equals C times AC cubed times the pressure gradient, where C is a constant that relies on the material of the formation, and AC is the conducting aperture, or in other words, the effective aperture. This equation is often used to gain better understanding of flow properties along with depth. So as we mentioned before, we cannot get the effective aperture unless testing is done, but after testings are done and the effective aperture is calculated, that value can help us understand how the geological formation is going to, or what the properties are more clearly, going deeper into a formation if there are technological limits that will not allow us to go deeper than where we have been. Now, these are two examples that I took from chapter 4 of the William E. Glassley book. So the first one discusses is asking, what would the fracture permeability of this rock be? And the rock that they are referring to is just a rock that has an aperture size of 10 microns. And 10 microns just means, the units of microns are just meters to times 10 to the negative 6. So here KFR, which is the fracture permeability, is a square over 12, which equals 10 times 10 to the negative 6 over 12, which equals 8.33 times 10 to the negative 12. So fracture permeability is a rather easy measurement to get once we have the aperture sizes. And what would be the fracture transmissivity of that same rock? Now, assuming most standard values work, this equation what I have presented here for 4.3 will work. So on top there you can see rho times g times a to the third, and that's why it's called the cube law, because it takes into account the cubic nature of these apertures. And this is all over 12 times mu, which is the dynamic viscosity. Again, here I'm using all of the standard values, assuming that the fluid we are looking at is still exhibiting standard conditions. But these values can be different, especially the density and viscosity, depending on how deep and how much pressure they've been exhibiting. But if we use these values that are presented, we get 9.158 times 10 to the negative 10. Hydraulic properties of real geothermal systems. Rock formations dominated by a pore matrix would require higher porosity to achieve a minimal permeability that results in sufficient energy generation. So, as we said before, how there are two different formations, or how we classify them for the purposes of geothermal energy. When a formation is dominated by a pore matrix, the porosity has to be high for this formation to be even considered. Now, it's not saying that if the porosity is high, we're gonna get the fluid flow that we want. It's only saying that if the porosity is less than a certain value, depending on the specific material of the formation you're looking at, if it's less than a certain, if the porosity is less than a certain value, this system is not worth looking at or not worth um, testing because it will not achieve the permeability required to get necessary fluid flow. However, rock formations dominated by fractures can be used for energy generation even with low fracture porosity as low as 0.2%. This is quite surprising, but the nature of fractures and apertures are longer than pore grains or porosity in pore matrices. So it's not very surprising that this is true. However, it just makes it more, I guess, difficult to determine if formation that is fracture dominated is worth it or not. So the limiting factors here are less. And finally, in conclusion, I just wanted to go through the main concepts discussed throughout chapter 4. Fluid flow in rock formations depends on pore characteristics and or fracture properties. So depending on whatever formation you are looking at, whether it is fracture dominated or pore matrix dominated, there are different characteristics. So for pore dominated systems, the main factors are interconnectedness of the pores, tortuosity, and surface area. We have discussed more than that in the characteristics, but these three are what really stand out in those kinds of systems. However, for fracture dominated systems, the main factors are apertures and everything that is associated with them, meaning their length, their interconnectedness, their roughness, the material of the rocks, their capillary suction potential, all of that. Capillary suction potential also is an important factor for matrix pore dominated systems. And for fracture dominated systems, the number of fractures is also an important factor. It is also kind of related to the interconnectedness of these fractures. One fact to keep in mind for both systems, fracture or pore matrix dominated, pressure gradient is always going to be an important factor. Like I said, it takes into account the viscosity, how much changes as you're going through a formation, what the temperatures experienced are, if the density is changing, if the viscosity is changing. This is something that will have to apply for any system that is related with geothermal energy extraction. Thank you.